Good afternoon, everyone. Welcome back to PH Faculty Speak. And we are happy to be kicking off this series this semester with one of our junior most colleagues, Athreya Shankar. It's my pleasure to briefly introduce him. Many of us have known Athreya as an engineering physics student here. I, of course, did not know him then, because some of us just joined when he left to do his PhD at the University of Maryland with at University had a postdoctoral stint at the Institute for Quantum Optics in Innsbruck, Vienna with Peter Zoller's group. And he was subsequently a C.V. Raman postdoctoral fellow at IISc, and he has been with us as assistant professor since July of this year. His interests include quantum optics, quantum sensing, and today he's going to tell us about a new approach to trapped ion-based quantum information processing.
Okay. So, can everyone hear me? Okay. So thanks for this opportunity to share some of my recent work. So, the title of my talk is Bilayer Crystals of Trapped Ions for Quantum Information Processing. So before I actually jump into this talk, I just wanted to give a broad research overview, and some of you may have seen this slide before. I just want to give a big picture idea of where I fit into the overall quantum technologies initiatives over the world and in India. So as we all know, quantum computing is the most fancied and famous application that is anticipated to come out of quantum technologies, but there are many allied areas where equally useful and probably sooner impact is expected, such as quantum communication, quantum sensing and metrology, and the simulation of one quantum system with another quantum system, which is usually called quantum simulation. So in this direction, there are experimental groups working on various types of quantum hardware. There's photonic systems, superconducting qubits. I'm going to talk about trapped ion systems. Many of our colleagues here work on platforms like NV centers and so on. And there's also the quantum software side of things, where people investigate protocols, algorithms, try to gain universal insights into the behavior of quantum mechanics itself. And a lot of the efforts here are largely system agnostic, and the hope is that they are like general guiding principles when designing experiments for quantum technologies. So I come right in the middle, and my work is broadly the use of quantum optics theory for quantum technologies. So my role is to interface quantum hardware and software and translate some of these probably abstract quantum algorithms to real physical processes on quantum hardware, and also come up with a bottom-up design given certain resources, some realistic constraints. We want to design concrete quantum information protocols within the boundaries of these constraints. And at the same time, I'm interested in analyzing various types of quantum hardware, such as the systems here, in order to exploit native features that these different hardware platforms might present, also build new capabilities in these systems, identify possible limitations, and if there are limitations, design some control and mitigation strategies to overcome these limitations. So this is where I fit in. So with that introduction, I want to switch over to my talk for today, which is about these trapped ion systems. And first, I would like to start with an acknowledgement to my research collaborators. It's very impressive to note that the first author on this work was actually a BSMS student in his 5th year when he started this work, and the second author is actually an undergraduate student still in IIT Bombay. And this is a collaboration between universities in India as well as people in JILA and NIST, which are both in Boulder, Colorado. So let me start with the motivation for this work. So trapped ions are actually a mature quantum platform for quantum information processing. As you may know, these are basically systems of charged particles that arrange into very nice crystals, where each of these charged particles is basically a single ion, a single atomic ion that can encode a 2-level system. And once you have a 2-level system, the entire world of quantum information processing opens up for you, and this is what people do. So today there are in principle 2 main types of systems people study: 1D chains, and some of these chains can be so large that they don't even fit on the slide I'm showing you here. and 2D crystals of ions. And as you might know from Earnshaw's theorem, you can't trap charged particles in a stable equilibrium with just static electric fields. There are two ways to circumvent this. One of them is that you apply time-dependent electric fields. The other is that you combine a static electric field with a static magnetic field. So the ones that combine a that use time-dependent electric fields are called Paul traps, and all these crystals you see here are made in Paul traps, even this two-dimensional crystal. This one is made in a penning trap, and the penning trap is going to be the focus of the talk today. So I will get into more detail in a few slides down this talk. So there's also some recent work from this year where some of the largest 2D planar crystals ever used for quantum information processing have been produced. This is a crystal in a Paul trap with about 512 ions. And this was actually also discussed in detail in the recent conference that we had in IITM as well. So if it's so cool, then what else is left to do? Well, the answer is many of these other quantum information processing platforms that I mentioned are moving towards multi-layer 3D architectures. For example, these are neutral atoms in optical tweezers, and a group has actually managed to make the Eiffel Tower by just arranging the atoms in a certain geometry. And this is also a certain example of stacking many layers over each other. These are the top views of different layers of a 5-layered 3D array. And you can see how you have different number of ions on different layers, and these are also moving towards on-demand geometries for atomic configurations in 3D. Penning trap architecture, because the penning trap is naturally suited to store a lot of ions. It's not very good if you want precise control, say I want to have 2 or 3 ions, then it's not such a great platform for quantum information processing. But if you are working with 20 to hundreds of ions and you don't really care whether it's 110 or 120, this is a terrific platform for quantum sensing and simulation. And since you already start with many ions, the question is, can we actually realize these large-scale multi-layer crystals on the penning trap as an alternative to these microfabricated RF traps? So the question is, like you asked, why should we go beyond 1D and 2D crystals? One of them is the natural answer is that there are now more ions, you can do more, get higher signal to noise ratio in any kind of measurement that you do. You also open up new toolboxes for quantum information processing, and I will give you concrete examples of what these new toolboxes are. And also, this notion of having bipartite entanglement between spatially separated ensembles. So this is actually something that's very much sought after in a wide variety of quantum information platforms, and some of these platforms go to great extents in order to actually achieve this. For example, in atomic BECs, people actually make atoms in a single lattice, and then in order to actually get to get a notion of two different spatial regions, they switch off the lattice, and then the gas expands, and once it expands, you can basically divide your region into A and B, and now you have a notion of two different ensembles, and then you can study bipartite entanglement between them. But here, if you really had from the beginning two different or multiple different layers, then you have this powerful capability of generating entanglement between ensembles, each of which could have many ions or atoms themselves. So that's the main attraction with multi-layer architectures.
Is there a theorem that there can be entanglement only between the vertical layers, not along the horizontal?
No. This depends on how or what your
system.
system.
You didn't answer me. Why do you need a 3D?
I will come to that. I will show you what is it that you can do in 3D that you can't. It will come a little later in the talk, but it will come there.
So again, apart from that, if we can increase from 512 to 1000, but won't you have enough freedom already? The 2 to the power 510 to the 12 or something like this now?
Yes, but sometimes, say I am interested in sensing a gradient signal, and then it's different at different locations, like a gravity gradient. Then I need physically the atoms to be in different locations. No matter how many I have in one plane, it's not good enough. So there are applications where you need this extra spatial degree of freedom. So that's one example.
Okay.
Yeah. So some marketing now. So this is our paper, and we got some nice coverage for this from Jilla, which had a nice write-up on this, and this was picked up by many news outlets as well. And very nicely, today if you open the IISc website, the first thing that you will see is our work. So this is on the IISc homepage right now from today morning onwards. So we got some nice recognition from both the institutes that...
It says COVID-19.
Oh yeah, that's... yeah, well, they managed to update the important part. So, okay. So I'll start with a brief introduction to ion crystals and penning traps. So what is a penning trap? I've been saying this word over and over again. So a penning trap is basically a system where you have a bunch of electrodes that generates what is called an electric quadrupole field. And in combination with that electric quadrupole field, there is also a strong transverse magnetic field in the Z direction. This magnetic field, when I say it's strong, it's about 4.5 Tesla. Okay, so the axial confinement of the crystal is given by the electric quadrupole field, which tries to push all the ions into the Z equal to 0 plane. But the radial confinement actually comes from a combination of the electric field and the magnetic field. And because of this combination, because there's a Lorentz force, this crystal is rotating all the time. And this rotation, if you just leave it as such, is not such a well-controlled rotation. So you have additional segmented electrodes. These are the ones that I'm referring to. And these electrodes are actually there to apply a very small time-dependent potential that's called a wall potential. And this wall potential is simply used to lock the crystal rotation frequency. So this crystal rotation frequency can be around 180 kilohertz. Whereas the axial trapping strength, which is again characterized by frequency, that's about 1.6 megahertz. So these are some important numbers, and the ions that we are typically looking at are beryllium ions, because these are the most commonly ones used in this particular trap. So the equilibrium is actually a balance of the trap potential and the Coulomb repulsion, and so far most experiments work in the regime where the axial confinement is very strong compared to the radial confinement. So because of this, the ion crystal basically spreads out into a nice single layer, and you can see this in the experimental images as well, where in the side view you just see a single plane, and in the top view you actually see this very beautiful lattice structure with a hexagonal lattice. And the inter-ion distance is typically about 10 to 15 microns, and the overall crystal has a radius of the order of hundreds of micrometers. So every beryllium ion here is actually, you can think of it as a spin half or a two-level system, and that's why this platform is amenable to all these quantum information processing protocols. The axial frequency, so there's a trapping force in the Z direction, and the strength of the trapping force, if you think of it as a harmonic trap, the strength of it is 1.6 megahertz. That's also, by the way, the center of mass motion frequency for this crystal in the Z direction.
Okay. So this triangular lattice or this hexagonal lattice, is this automatic or you can control it also?
This lattice structure, it is what you get. It's hard to control that. Yeah.
So if you change beryllium to something else, will it be different?
No, in this single plane configuration it will always, yes, but in the two plane configuration that I will show you, you can get a different structure.
And you usually need some case-wise atoms, right?
You need a what, sorry?
Some case electron atoms.
You mean a single valence, that is the most, that's the one people normally use for, if you have a single valence electron, things get simpler to deal with. You can isolate this two-level system. That's why in neutral atoms you use rubidium or cesium, but in ions you use beryllium, magnesium, calcium. So because they have a charge. That's right. One valence electron, yes. Okay, so let's see how to get to two layers now. And the general theory, and this was worked out in the 1990s by plasma physicists, is that the key parameter is something that we call beta, and this is the strength of the radial trapping strength to the axial trapping strength. Now note that the radial trapping strength is the trapping strength in the rotating frame of the crystal. Remember, I told you that in the lab frame the crystal rotates at 180 kilohertz. So this is actually, when you look at it in the rotating frame, it looks like a static crystal, and in that frame the trapping strength is given by this omega perpendicular. And the important feature is that it depends on the rotation frequency itself. And the condition for a single plane crystal is that this beta must be smaller than a critical value, and this critical value scales down as 1 over square root of the number of ions in the crystal. So one natural way to try and go beyond a single plane crystal is simply to increase omega perpendicular by spinning up the rotation rate of the crystal, which increases the radial trapping strength. So I'll show you a movie about what happens as you spin up the crystal. So you're going to see three things: the side view of the crystal, the top view of the crystal, and the histogram of Z positions as you histogram the locations of the different ions. Okay, so now we're going to start with beta over beta C of about 0.19. There are 200 ions in the crystal, and we're going to see what happens as this ratio crosses 1 and increases beyond 1. So, okay, that was an anticlimax, it didn't play. Let me try to play it. Okay, so there it is. So as I spin up the crystal, as I increase the rotation frequency, you can see that it still stays a single plane, but at some point ions start popping out, and then beta over beta C is greater than 1, and you start seeing ions in more than just the central layer. You have actually now a clear notion of, not clear notion, but some notion of there being 3 layers in the crystal. That is what you see. But the main point is that if you look at the central layer, in the top view, all the ions in the central layer are actually on the boundary. So the correct way to think about this is that there are 2 layers that kind of taper off at the edges into a single layer. And it turns out that if you actually work out the theory for this in the thermodynamic limit, you can actually show that there is a clear 1 to 2 plane transition in the system. But because we have a finite number of ions, these are what you're seeing here are finite size effects. And the question is, with a finite number of ions, and typically 200, 300 is the kind of numbers people can work with these days, can you still get a clean bilayer crystal? So now that we looked at the harmonic case, you can look at what happens at different beta over beta C values. So when beta over beta C is above 1 but not too large, you can see that from the side view there are 2 layers that taper in, and now Titas, to answer your question, you actually have in the center a square lattice, a staggered square. So if you look at any of the blue ions which are in the bottom layer, they form a square, and so do the green which are in the top layer. But
perhaps an analogy to, for example, the vortex lattice physics, where you get square or hexagonal lattice associated with this.
it might be, I don't know, I'm not sure.
And another thing is that when you introduce rotation, you introduce a chirality, right? So does that get accounted for in the quantum mechanics of the problem?
There are ways in which you can use that chirality.
Okay.
I will show you some examples of chiralities that come up, and that's because of the B field being upwards that introduces a chirality. I will show you some examples of
So
this.
the top layer is actually rotated in reference to the bottom layer?
Yes, it is. Yes, it's rotated. It's staggered.
It seems to be very nicely rotated, like 150 or 60 degrees, right?
Exactly. You can see the bottom layer in the voids center, in the voids of the
It
top
comes
layer.
naturally.
It comes naturally. And you can predict this from this plasma physics theory as well.
This is classical.
This is classical. Everything is classical so far. The quantum is yet to come. But the nice thing is that there's another prediction that classical theory makes, which is if you make this beta over beta C larger, you actually transition from a staggered square back to a hexagonal lattice, only that it's again a staggered hex lattice. But again you see that there is a taper, and this is not really such a great bilayer crystal at all in that sense, because you still have many ions stuck here, and this is not really a single layer. So there are many issues with this. So we continued our quest to form these clean bilayer structures, and it seems that if you have a purely harmonic trapping potential, you have strong boundary effects. But
This transition from a single layer to a bilayer is a natural phase transition?
in the end tending to infinity
In the end
limit,
tending to
yes,
infinity?
it's a structural phase
It's a
transition.
structural phase
Yes,
transition?
actually you can go from 2 to 3, 3 to 4 and so on, and each one is a phase transition.
Each one
Yeah.
is a phase.
And then in the large layer limit you get the genuine 3D structure with a BCC lattice and so on.
But this cannot happen in your pending graph system.
It can if you have more ions, but then it's not very useful for the quantum simulation because they can't control such large systems. So the natural question is, how can we mitigate these boundary effects? And the first thing that we tried was, okay, if the harmonic potential is a limitation, let us add a small amount of unharmonicity. And there was a bit of motivation to this in the sense that in RF Paul traps, usually the equilibrium spacing between ions in chains are uneven. And in order to make the spacings more even, people have added unharmonic potentials before and have made the spacings even. So we thought, okay, if it can clean up the structure in a RF trap, why not try it with a bilayer and a penning trap? And this is the form of the potential that we added, and you might ask, why do we add it in this particular way? And the reason is that this is the only thing that you get, because this is the only quartic term, the form of the quartic term that you can have that satisfies Laplace's equation. So this is what you can actually apply in practice in the lab. So now another movie which will show us what happens as we increase the strength of the anharmonic potential. And here, as you increase the strength of this potential starting from a bilayer, I want you to see the side view as well as the histogram as the C4 bar hits close to 1.5 or so. And then you will see that very dramatically, actually the crystal starts cleaning itself up. And then at some point in the middle, you might have noticed that there were almost like no ions in the middle and only two very clean layers. And this is what we call as we consider to be like a sweet spot for this system, where you can have two very clean layers of trapped ions. So over here, yeah, any questions at this point? No? Okay. So there's an intuitive explanation for why adding an unharmonicity helps, and you can think of it in terms of basic electrostatics. So the axial trapping force which is coming from the electrodes is actually a force in the z direction, and these are the two layers that we are looking at, and this force is actually independent of the distance from the trap center. But if I take two disks and ask for what is the Coulomb repulsion between two disks, what happens is that the Coulomb repulsion is maximum at the center and starts tapering away towards the edges. And this is why, no surprise, in the harmonic trapping case, you actually got two layers that were actually bent or tapering inwards. Now, the role of the anharmonic potential is that it gives, through this cross term, the z square rho square term, z directional force that actually increases with radius, and that basically compensates for the tapering of the Coulomb repulsion, and that is why you actually get two flat layers when you apply an anharmonic potential.
So this is an artifact of the finite size.
Yes, that's right. If those disks were infinite, then yeah, there is no notion of an edge, and these arguments don't work.
Not only infinite, but long, if it is large enough, maybe at the central portion.
In the center, yes, you're correct. That's right. But there are reasons we don't want to do that. But there are reasons why we don't want to do that. But I'll explain that offline. Yeah. Okay. So the best case system at an optimal value of this unharmonicity strength looked something like this. Basically, had two layers of ions separated by about 10 to 12 microns. And there were still some ions in the middle that we just called scaffolding ions, because it's like the scaffolding that is supporting the bilayer structure. And it had a staggered hex lattice, again like one of the harmonic bilayers. But the nice thing is really that we now have spatially separated ensembles, and there are about 80 ions in each layer roughly. So now let me move on. Yeah. It's a good question. We didn't really look into that too much, because applying a fourth order term this strong is already challenging. But we expect that if you go to higher order, you can clean it up further.
I meant to say you have to machine that surface, which is fourth order, or you have to make the electrode that shape.
Oh no. So what you can do is you can control the lower orders, because these are electrodes that have independent voltages applied. So you have a few degrees of freedom, which means on how much voltage you apply, which means you can control a few of the harmonics, and then they anyway decay very rapidly, so then we don't care so much.
Are these experimental data or?
No, simulations. Everything, we are only showing a way, we didn't make the way. Yeah. So, yeah.
The scaffold, in terms of dynamics, the scaffolding ions, gaseous, compared to?
So this is actually a point of stable equilibrium. This is a minimum, this is a point where you should only expect a small amplitude motion about the equilibrium positions. Yes, in the rotating frame. It is frozen in the rotating frame. Yes. Yes.
So, how do you individually address the ions when they are like separated into
We won't address the ions individually. It's actually very hard to do that on this trap. So it's not a good device for a quantum computer. But there are many quantum simulation and sensing protocols where it's enough if you can image each layer on its own. You know, like I know the total spin state or observable. I don't know it on every ion. That's enough for many applications. So, okay. Okay. So let me move on to the normal modes. How much time do I have? Did I? Half an hour. Great. Okay. So I want to talk about the small amplitude motion about the equilibrium because this is a very important component of ion traps. So because it is actually these normal modes of vibration that are actually used for coupling one two-level system, which is one of the ions with another ion at a distance. So the general idea is that these modes are basically harmonic modes which when you cool down to close to their ground state start behaving like quantum harmonic oscillators. That means that in some sense they are equivalent to providing a bosonic channel that couples to all the ions in the system, and that means that there is a common degree of freedom to which all the ions talk, and this is the way that you can engineer interactions in the system. So these normal modes are actually very important to understand in any trapped ion system. One complication in the penning trap compared to the Paul trap, which is the RF trap, is that you have a magnetic field. And what that means is that the canonical momentum is not the same as the mechanical momentum. And that means, although this is harmonic motion, it is not your usual simple harmonic motion where the restoring force is proportional to the displacement from equilibrium. So because of this, you get very interesting and complicated modes, and therefore one has to be careful in both the treatment and in deciding which modes are actually useful for doing any interesting protocols. So usually in these crystals there are three mode branches, and first I want to talk about the single plane case, the single layered crystal. And these are basically, there are two branches of planar modes and there's one branch of out of plane modes. The planar modes have a low frequency E cross B mode branch where these are low frequency modes that are attributed to the fact that there is a drift of charged particles when there is simultaneously an electric field and a magnetic field. And then there are high frequency cyclotron modes where the ions are having rapid motion, and that's purely because of the magnetic field. And then in the out of plane direction you have what we call as drumhead modes, because it looks like a membrane of a drum, except that even the boundaries are not fixed, even the boundary is moving. So these are called the drumhead modes. So this rough mode structure, as you can see here, for 200 ions you have 600 modes. So this is the low frequency component, and it's usually it ends at around few hundred hertz, or actually only about 150 hertz. And then here you have the drumhead modes which are of the order of a megahertz, and then you have the cyclotron modes which are of the order of 7 megahertz. And the nice thing is that when we go to this bilayer crystal, the mode branch structure is roughly maintained, although now you can see that the gap between the drumhead and the E cross B modes has come down. But to get a better feel for these modes, because these are the ones, the drumhead modes are the ones that are used for the quantum protocols, it's nice to actually have some kind of visualization. And here I'm showing you some of the first few high frequency drumhead modes. So these modes are, the first one I'm showing you here is actually the center of mass drumhead mode where all the ions move in phase. And then there are two tilt modes, and in these tilt modes you can see that one half of the crystal moves out of phase with the other. And then there are these Lay's or Pringles type modes as well, where you can see the deformations are like potato chip deformations. But the in-plane modes are far more complicated, and here is an example of some of the E cross B modes, which I will play with my mouse. Okay, so these are some E cross B modes. Some of them are easy to interpret. Here, this is just a rocking of the crystal in the crystal plane. And all of these modes are actually in the rotating frame. So in reality, in the lab, there's the crystal rotating, and on top of the rotation, you have all these modes superposed as well. And the cyclotron modes similarly are going also as rotational motion, but now the rotation is mostly in the opposite sense. They are counterclockwise modes. And I should also remind you that this happens at about 100 hertz frequencies, but that happens at around 7 megahertz
Can I
frequencies.
ask you something, sir?
Yeah.
So, does this actually create some topological vortices and something like that?
No, so actually the physical ions are not moving. Every ion,
So, this is not physical.
the ions are sitting where they are and making small orbits, and the arrows, the tip of the arrows are showing those orbits. That's all.
So they look like so-called magnetoroton modes.
Yes.
Yes, that's right.
Quantum modes.
Yes. But for most of the quantum information stuff, these modes are not used, the in-plane modes, because as I told you, the crystal is rotating in the lab frame and accessing these modes are challenging. But the out-of-plane modes are frequently used. So now let's go to the bilayer case and look at what the modes look like there. And I'm only looking at the drumhead modes. And here you have a variety of drumhead modes, some of which are simply analogs of single plane modes. You have modes where there's a breathing motion happening, and then you have modes where, sorry, I need to play this again, where you have a center of mass motion of the entire crystal. And the most interesting modes here are these two modes, which actually point to a new feature. So if you look at these modes, every ion is only moving up and down, but if you stare at it long enough, it gives you the sense that the crystal is rotating, and that's because the phase of the disturbance is propagating in a certain direction. And this is a feature that does not arise in single plane crystals. In other words, the new feature in bilayer crystals is that the drumhead modes have a broken time reversal symmetry. If I were to play those normal mode movies to you backwards in time, those two modes would actually look opposite of each other. And so one can actually define a measure of chirality for how much time reversal symmetry, I mean, to kind of quantify to what extent time reversal symmetry has been broken. And the main new feature with these modes is that in the anharmonic bilayer case, you actually have many of the out of plane modes actually breaking time reversal symmetry. So this is a new feature we uncovered with these two layered crystals. So with that, I want to move on to the quantum applications of these kind of systems. So again, how do you actually use all these features of the ion crystal to do any kind of quantum physics? And for that, it's better to first look at single plane crystals again. So this is your planar crystal, and one of the workhorses of this trap is something called the optical dipole force. And the way the optical dipole force works is that you have two layers that cross each other such that their difference wave vector is along the z direction. And the net result of this is that one of the lasers is at frequency omega and the other is at omega plus mu, and because of this you have a traveling wave optical lattice in the z direction. And the role played by this traveling wave optical lattice is that it leads to a stark shift on the ions in such a way that the magnitude of the stark shift actually depends on where the ion is located. So you can either view it as a position dependent AC stark shift, or if I take this Z outside, you can think of it as a force on the ions that actually depends on the spin state of the ion itself. So it's either a spin dependent force or a position dependent AC stark shift.
The quantum character comes through the spin, electron spin.
There are two ways it comes in. One is that it comes in through the spin, and also the fact that these are ultra cold ions, so the motion in the z direction is also quantum mechanical. So it comes in both ways. And now I want to remind you again of the fact that, as I said, the motion in the z direction can be decomposed into those normal modes I was talking about. And once I write it in terms of the creation and annihilation operators for the normal modes, it looks basically like a spin boson model. Now this particular kind of coupling Z sigma Z is a very, very special coupling. The reason is that this difference frequency between the two lasers, this mu parameter here, is a control parameter that helps us decide which mode I want to couple to out of the various normal modes in the system. So if I take this mu to lie close to one of the modes, then I can basically ignore all the other modes, and the interaction between spins is basically controlled by that one mode or the modes closest to that frequency. So If I isolate one of the modes, then what happens is that at very specific times, when the delta times tau is a multiple of 2 pi, you can actually show that the motion basically serves the role of mediating an effective Ising interaction between the spins at these very specific times. And this coefficient of the Ising interaction depends on the parameters of the spin dependent force and the detuning between the ions. That means that if I start from an initial product state of the spins, it can actually lead to entanglement of the spins through the course of the evolution under this effective Ising model.
So Z is the Z coordinate with reference plane.
That's right.
So it changes sign. It's as if the Zeeman field is changing signs as it moves up and down.
Yes, that's right. It's an operator. So in some sense, the ion is everywhere. Yeah.
Given.
Can you make a system local because this is entirely non-local, right?
It is possible. Like you want. I mean, are you asking? Can I make this JJK? Yes, you can tune it from, not in this way, there's a different way, but you can tune it from all-to-all coupling to 1 over R cube. That's the range you usually get on this system.
Can you put a transverse field on it?
You can, and I'll show you what happens. So what happens in the bilayer case? In the bilayer case, there's a new twist to this spin-dependent force, which comes in the fact that now there is an extra phase associated with each ion, and that extra phase is simply the fact that the equilibrium configuration is not the z equal to 0 plane, it's actually two different planes. And that means that there is now an extra control parameter in the two-layer system, which is the mean interlayer phase difference. It's basically, the physical picture is, it is the phase acquired by the optical lattice at a given time as it travels from here to the other plane. And that basically is proportional to delta k, the difference wave vector of the lattice, and the delta k in turn is controlled by an experimentally controllable parameter, which is the angle at which the two lasers cross each other. So the delta k is actually something that is in your hands as an experimenter to adjust.
So there is no way I can get an effective theory which is not ZZ but Z dot Z. There's no way I can do that.
You mean sigma dot sigma?
Yeah, sigma dot Z.
There might be ways by trotterizing and things like that. Yeah, not directly.
Not directly.
It's not the native operation. Yeah. Okay, so I want to show what happens because of this interlayer phase, which is controlled by the tilt angle. So let's say that the tilt angle of the ODA lasers was around 10 degrees. I take two parameters around 10 degrees. And in one case, and what I'm plotting is a histogram of the JJK coefficients, the number of ion pairs that have JJK coefficients of a certain value. And sorry, I'm not plotting the JJK coefficients, I'm plotting simply the relative phase difference of the ODF lattice at the location of the two ions. And this histogram in one case basically peaks at 0, and that's because the interlayer phase, I have tuned it to be 0 by this choice of angle. And in the other case, it peaks at two different locations, basically at 0 and pi. But as you can see, it's really very noisy, and that's because although I told you there are two layers, the truth is the two layers still have some noise. It's not a very perfect layer. And therefore, if I make the ODF lattice too steep, then my lattice does not really resolve the layers in some sense. The layers still look very noisy. But if I go to a smaller ODF angle around 1 degree, then you can immediately see that I have very clearly defined interlayer phases. For example, here the interlayer phase is 0 and here the interlayer phase is 180 degrees. And what that means is that the interlayer Ising interactions can be controlled, because now when J and K belong to different layers, there is a cos phi, which is the mean interlayer phase difference that enters this expression. So what is the big deal about this? The big deal is that while the intra-layer phase is always going to be 0, and that means the JJK coefficients are always positive, that means the intra-layer interactions are always going to be anti-ferromagnetic. The interlayer interactions can actually be tuned all the way from anti-ferromagnetic to ferromagnetic, and there's a special point when it's 90 degrees that you can even turn off the interlayer coupling. That means there are ways in which I can set up the experiment where the two layers basically don't know each other's presence simply because the ODF lattice traveled 90 degrees between them. So that's something, and these different kind of dynamics can actually be readily distinguished by actually studying the mean field spin precision of these spins in a practical experiment. I won't go into those into the details of that part, but there's one more icing on the cake that I want to talk about, which is the fact that in the previous example I said that you can control the interlayer phase by actually changing the tilt angle of the lasers, but that means that between experiments, as an experimenter, you have to go in and actually change the angle of certain mirrors so that they cross at different angles and so on.
Acha, do those angles that you get, does it happen at special angles or is it a range of angles?
This angle, the angle between the lasers, yeah, this you can tune continuously.
But those regions,
these happen at specific values of,
specific value.
yeah.
It's not a range of angles, right?
There's a continuous tuning. You can tune continuously this phi
But to get these scenarios, it happens
at specific values. That's right. Okay. So the question is, between experiments now I have to go change the angles of mirrors and so on. So the obvious question is, do I really have to do this? Can I not actually in a single experiment change the intralayer to interlayer coupling strengths and so on? And the answer is yes, you can, and you can do this by using optical control. So for that we use the fact that, remember I showed you these two different modes called the center of mass mode, where the two layers move together, and the other mode where they move out of phase. So we can actually use these symmetry properties to actually control the interlayer and intralayer interactions on the fly. And the way to do that is to see that, first of all, if I use only the center of mass mode and I'm keeping the interlayer phase to be 0 for now, then what happens is that if I only have one optical lattice that's close to the center of mass mode, then for all the ions belonging to either of the two layers, which is the orange box here, the JK coefficients are pretty much similar. They are positive, and about, for the time we chose, they are about 0.01, whatever that means. Okay, so but if we use the breathing mode, then within the layer the ions are moving in phase, but across two layers they are moving out of phase, and therefore the interlayer coefficients can be made negative. But now I can actually apply two tones of my optical dipole force, and when I apply two tones and they have equal magnitude and are applied in phase, I can basically cancel the interlayer coefficients. On the other hand, if I have two tones but I tune the second tone to the red of the breathing mode, then I can basically cancel the intralayer coefficients. So what that means is,
time dependent
which one?
phenomena what you're talking. Because you're controlling by exciting the mode.
It will be, but we are analyzing the dynamics, the effective dynamics at tau equals delta tau is 2 pi. At specific stroboscopic times, you have an effective Ising model. And so now, by simply changing the magnitude and detunings of these two tones that I apply, I have continuous control on whether I want the interlayer interactions to be there or the intralayer interactions to be there, and the relative magnitude and phase of the two. So this way, in a single experiment, you could go from having both layers interacting with each other to having both layers only seeing each other, to having both layers only seeing the other one and not themselves. So you have a whole range of control possible with this technique. And so the last control part I want to talk about is what happens when you add a transverse field. So usually a spin exchange interaction looks like this. Okay, you have two spins and they flip-flop their excitations, and you have a coefficient that sits in front. And what you need for this is an Ising model with an extra transverse field, such that the counter-rotating terms drop out and you have only the exchange terms. What happens in the case of the bilayer is that you can actually get chiral spin exchange. What that means is that the coefficient for flip-flopping from J to K and flip-flopping from K to J can actually be different from each other, in the sense that they can be complex conjugates. And the reason why this can be made possible is once again the fact that you have this interlayer phase phi. So what happens because of the interlayer phase is that you actually have now a real part that's controlled by the cosine of this interlayer phase and an imaginary part that's controlled by the sine of this interlayer phase. So as I change my tilt angle, as I told you, you can change this interlayer phase from 0 to 180 degrees, and you can basically look at what happens to the spin exchange coefficients when the ions are in the same layer, in different layers, and when they are not belonging to either of the two layers, which means they are in the scaffolding. So when phi is 0, the coefficients are all real, but then when I go to, for example, phi 90 degrees, I can make the interlayer coefficients basically imaginary compared to the real coefficients intra-layer. So this way I have again continuous control over whether I want a chiral model or an achiral model in my system based on my application. Yeah, it looks like a bird in flight, yes. Yes.
So can I ask you, so I'm slightly confused with this I B term in there. Is this like having some sort of non-Hermitian version of?
No, it is still Hermitian.
It's still Hermitian.
It is still
Because
Hermitian.
there is a J star sitting.
Exactly.
And if by some reason I can change my J and J this thing, then I can get.
Then it becomes non-Hermitian, but I can't do it with the ingredients I have. I need an environment or some dissipation.
Okay.
Yeah.
Yeah, exactly.
Okay, so why is all of this a big deal? Because it opens up the route to many potential applications. For example, you can study the preparation and applications of what are called two-mode squeeze states, where you can actually have squeeze states that actually have correlations across the two layers. Those kind of states are useful, for example, in quantum metrology, where one application, as I already mentioned, is that you want to sense a gradient, a 2-point gradient, and now you have two layers with many ions in each layer. The other interesting thing is this on-the-fly control I mentioned is very useful for what are called variational quantum circuits. Say you want to build a circuit where I want to first entangle spins within each layer and then across the layer and then again only within each layer. Then you can actually use this optical control you have in order to prepare states with different ingredients in your quantum circuits. And these states are shown to be useful for sensing, say, a magnetic field which can have more than one component in the signal. The other interesting application is that since you have many ions in each layer, say about 80, you can think of this as a very large spin, as a very large mean spin, and then you have small fluctuations around this mean spin. And that means that very locally, a spin can be described on a sphere, but if the sphere is very large and you have very small fluctuations, locally the spin looks like a plane, the sphere looks like a plane, and then you can think of it like a harmonic oscillator, very locally. And therefore, you can actually do continuous variable quantum information where the components perpendicular to the mean spin basically look like the x and p quadratures of a harmonic oscillator. So that's another application that's possible. And then because I have chiral exchange interactions, there are some natural connections to models in condensed matter physics, but there are too many condensed matter physics experts, so I'm not going to open my mouth on these things. So, but anyway, so with that, yeah.
So can you get coefficient between the two types? These are macroscopic divisible, right?
Yes. What do you mean? Like again, in the notion of this continuous variable thing, you can identify Sx. Say your spin is along Sz. You can identify Sx, Sy as x and p.
These are macroscopic divisible, right? They will decay very fast.
No, because these are not in the sense they are not known states that you are making. These are not known states that you are making. You are still close. You are only mildly squeezing the states. So in that sense, the decoherence that you have are all single particle decoherence. They will decohere fast, but you can still. I think that you can overcome decoherence at least at short times.
Spin coherent states, essentially.
You start with spin coherent states, but then you apply a small amount of squeezing on these systems. Okay, so with that I want to go to the last section of my talk. I have another few minutes. Okay, great. So one thing that we realized was actually this technique can be extended to create more than two layers, like for example a tri-layer crystal. But we haven't really explored, what we can actually, how the normal modes look like and other aspects of the system. But it seems like once you get to a bilayer in an experiment, this is like a natural next step for somebody to try. And then maybe what you can do is call this as Alice, Bob and Charlie and try a continuous variable quantum teleportation experiment between these different layers. Okay, so with that, I mean, I will display this summary again, but maybe I wanted to point out before doing the summary about some of the other things that I work on beyond trapped ions, and that brings me to this slide, which also some of you might have seen before. So as I said, I'm very interested in quantum sensing and metrology. This is what I did for my thesis. How do you prepare spin squeeze states? How do you read them out? How can we embed these states into real interferometers where things like dissipation is a challenge, which means can we actually use dissipation for as an ally instead of something to be afraid of? Can we, for example, engineer dissipation so that we can stabilize some states of interest and use them for some sensing applications? And I'm always interested in how can we develop new toolboxes for existing quantum hardware, and one example is the talk that I gave today. And I'm also interested a bit in analog quantum simulation, where I'm interested in mapping models that are of interest to someone like Titus, like condensed matter models, onto systems like trapped ions as well. So if there are any masters in UG students in the audience and you feel this kind of stuff is interesting, please do contact me. And the final thing I want to mention, in case you don't know, is the next year is actually the International Year of Quantum Science and Technology, as declared by the United Nations. So I feel personally that as a department we should have many initiatives celebrating this year. So I'm always open to discuss and see if any interesting ideas will work out on this front. So with that, I'll leave you on the summary slide, and thank you very much.
Few more questions.
How close did they come to making it? This one model.
Yeah, this is all simulation. So there are already many experiments on the single plane crystal. With the two planes, one thing is that the kind of unharmonicity strengths that we need, they're quite strong. And when people actually build these traps, most of the time the goal is to lower axial frequency. You might be able to see two layers with lesser demand on the voltages that you want to apply. So I would say in 1 year's time, there's an experiment at NIST where I showed those images of the crystals. Maybe in 1 year's time, they will be in a position to try this with 3000 ions.
And how close can you bring those atoms at all? I know yours is more like but with the layer.
Within the layer.
Within the layer.
So usually it's 10 to 15 microns, and if you try to make it too close, what will happen is it will simply pop into a new layer. So there is a limit, you can't bring them. Yes, so then it will just become another layer. Yes.
What voltages are you having in mind when you said?
So the typical voltages that are applied on this system are like 2000, 3000 volts on this. No, static.
That should be very good.
But that is for the harmonic trapping. For the anharmonic, it starts going up to like 5000, 7000, and then they start worrying about crosstalk between the electrodes and things like that.
Is the trap always at like 4K or something?
Yes, I think, I don't know if the entire, that's a good question. I don't know if the entire trap is at 4K, but there's a superconducting magnet that gives you the 4 Tesla field. That is definitely at Kelvin temperatures.
But there is also black body radiation at room temperature which heats your trap all the time, right? So in these models,
The ions are laser cooled. Before every experiment, the ions are laser cooled. You basically cool them down by Doppler cooling, and then you do sub-Doppler cooling, and then you start your experiment. And your experiments are a few milliseconds typically. And then the next shot you again cool and start.
so there is then a lifetime for the ion in the trap.
No, in the trap it's very stable because the background, it's in a vacuum, so background gas collisions are minimal. It's just that they get heated up, and then they may, they may not be the best because you're using the motion for the quantum protocols, you may not be able to preserve the coherence of those protocols. That's why you need to cool them. But the crystal itself is very stable. For hours, you can keep the crystal. With beryllium, there's another complication, but I'll tell you later.
Traps for precision spectroscopy, they always maintain them at 4K. The electrodes are not just the.
Yeah, this I don't know the answer to this
I
question.
was wondering if, because you said it's quite cool.
Yeah. Okay.
I was wondering about
I'll take that question first.
twisted bilayer, because there's a lot of interest about twist.
Yes.
Why did you twist?
Okay.
It's already twisted, right?
No, but it's not controlled twist. It is what we get. And everybody has asked me this question at the end of a talk, and we don't know how to make twisted bilayers. We only know how to work with what we get. We don't know what is the ingredient that will
The
lead
idea
to
is
work.
to make that mode soft, that particular mode soft, so that it gets frozen. Anyway, we'll discuss it.
Okay. Okay.
Thank you.
So you had mentioned that you'll be working at ultra cold temperatures.
Yes.
So will Doppler cooling be sufficient, or do you want to take it to like the actual like motional ground state? So
That's an excellent question. Doppler cooling is enough for many protocols, but not all protocols. So I'll give you some numbers since you asked that question. So Doppler cooling takes you to about 450 microkelvin, which with this 1.6 megahertz frequency, which that means that if you think of your center of mass frequency as a motion as a harmonic oscillator, the mean thermal occupation is like 5 quanta, 5 phonons roughly. Okay. So in 2019, my second encounter with the Penning trap was actually a proposal to ground state cool this system, and they did the experiment, and actually we have a paper where we actually go down, we show that the center of mass mode we cool down to n bar of 0.3, which is like 50 microkelvin. So we can do it. It's just that integrating that protocol with the other protocols has so far been a bit challenging, because when we cool this mode, these modes, something strange seems to happen to the other modes, and we don't know what that is yet. Yeah.
Just for piece of information, this morning I was visiting Arvind's lab.
There are no further questions. Let's thank Athreya again for a wonderful talk. And can I request some of the youngest members of our audience to hand over this moment.
Somebody should take it. Thank you. Let's smile. Thank you.
Thank you, sir.
Thank you, sir. Thank you. And we have tea served outside, I believe.